Okay, so finally at homological mirror symmetry. So recall we had some closed string invariants, which were Gerstenhaber or BV algebras. Which were quantum cohomology and symplectic cohomology, where the difference was this one counted spheres like that and this one counted surfaces like that. And we had let me put an extra line in here. Open string invariance, which was an A infinity category. And that here was the Fukaya category of M, which counts disks with boundary punctures. Or if you want to make it look more like this, it counts surfaces like this. So these are the closed strings, these loops, and these are the open strings, these kind of chords. That's where the name comes from. And we had the B model was the tangential cohomology, sheaf cohomology of the sheaf of multivectors or polyvectors. Or if we had a Landau-Ginzburg model, a variety is equipped with a potential, then it was this but there was a differential on this complex of sheaves, which was bracket with the potential W. And now what we're going to talk about today is what goes down here. Which is the bounded derived category of coherent sheaves, and also the category of singularities, which is defined by Orlov. It's an analog of this category of coherent sheaves where you have this potential on your variety. And the relationship between these was that there was this map, a closed open string map going from quantum cohomology to the Hochschild cohomology of the Fukaya category. Or in contexts where the symplectic cohomology is the appropriate closed string invariant, then it's a map from symplectic cohomology to Hochschild cohomology of the Fukaya category. And we expect these guys to be isomorphisms of Gerstenhaber or BV algebras or whatever the correct algebraic structure is on these closed string guys. And analogously over here, there is going to be a map from our closed string sector, our tangential cohomology, to the Hochschild cohomology of our open string A infinity category. And the reason I've written tildes here, I'll explain today. That the point is that this notation is usually referred to a category, but for this to work, we really need to look at some enhancement to a DG category, which is a special example of an A infinity category. So the Fukaya category was an A infinity category. So if we write Hom spaces as f of L0, L1, as the Hom space from L0 to L1 in this category, there are structure maps mu s looking like that. Satisfying the A infinity relations. Yes?
In the end, there's going to be some A and B relation, is that right?
In the end, we're well, maybe I can just how far ahead?
Sorry, I'm not.
No. So homological mirror symmetry says if M and M check are mirror varieties, or varieties with potential, or whatever the case may be, homological mirror symmetry is going to say that if we have varieties which are mirror to each other, then there are quasi-equivalences of A infinity categories between some derived version of the Fukaya category and the bounded derived category of coherent sheaves, and vice versa the other way around. And one of the things you would like to say, but is, maybe is not completely understood in the literature at the moment, is how you go from this statement to say, well, these categories are equivalent, therefore their Hochschild cohomologies are isomorphic, and therefore these closed string invariants are isomorphic. Did that make sense, or did I say it too quickly? So maybe I can say intended corollary.
So even this is intended, right? HMS says this in certain examples at the moment. But
Yes.
Yeah.
HMS says there are lots of examples of varieties M and M check for which this is true.
And the A side seems to be all symplectic geometry, and the B side seems to be all algebraic geometry.
That's correct, yes.
So is this okay?
There, yes, so mirror symmetry is about saying there are pairs of varieties where all the symplectic invariants on one side are equivalent to all of the algebraic geometry invariants on the other side, and vice versa.
And what was the statement that you made after that?
That
What do you mean by intended?
I mean that this is not hoped for, yes. Hoped for corollary. Is closed string mirror symmetry. All right, well, I should really put so if these categories are equivalent, quasi A infinity quasi-equivalent, then you get equivalences of their Hochschild cohomologies. Well, I mean, this is a corollary, but, and now you have an isomorphism between quantum cohomology in this guy and tangential cohomology in this guy, where this comes from HKR, this one comes from the closed open string map, and the other way around too. What I say is intended or is only partial is, for example, checking that this guy is an isomorphism and checking exactly how much structure this isomorphism preserves so that we can extract all of the invariants such as curve counts that we want to out of this statement. Because it's certainly not automatic that if this quantum cohomology is abstractly isomorphic to a tangential cohomology as Gersten-Haber algebras, that you can extract from that all of the Gromov-Witten invariants that you would like to extract from mirror symmetry.
So it's like you do geometry and symplectic geometry to prove these equivalences.
Yes.
And then you do category theory and algebra to get from that the other stuff.
That's right. The hope is that once you've proven this thing for the categories, that everything else will follow by a general machinery. I mean, yeah, one needs, it's a little bit more than an equivalence of A infinity categories, but A infinity categories with a little bit more structure and so on, but that's the idea, that one reconstructs these Gromov-Witten invariants and things. Okay. Okay, so examples of A-infinity relations included mu1 is a differential on each morphism space. Mu2 satisfied the Leibniz rule with respect to this differential. The next one said mu2 was associative on the level of cohomology, and so on. So this allowed us to define the cohomology of this category. Which is an actual category, nothing A-infinity about it. Okay, sorry, so this is called the Donaldson-Fukaya category. So the open string B model has objects, coherent sheaves on M, or maybe I should say bounded complexes of coherent sheaves. Which, for example, you can think of as holomorphic vector bundles on complex submanifolds of M. Morphisms are the X'd groups between two coherent sheaves. These are some graded morphism spaces. And composition is composition of X's. Which, to fit with the notation I was using for the Fukaya category, will write like this. Okay, so this category is called dB co of M. Well, if you only take the subcategory of degree 0 X, i.e. HOMS, then it's the bounded derived category of the abelian category of coherent sheaves on M. Okay. This is the analog of the cohomology category of the Fukaya category, this Donaldson-Fukaya category. The analog of the Fukaya category itself, which is an A infinity category, is some enhancement of this bounded derived category of coherent sheaves. Which we'll write with a tilde to remember that it's not just the same as dB-co, it has more structure to it. The objects are the same. But the morphisms now are going to be the complex underlying your calculation of your X groups. For example, you could fix injective resolutions for each object in your category, and then define your Hom space to be just ordinary Hom of complexes between these resolutions. And then we have A infinity maps mu1 is the map from a Hom space to itself, that's the differential which you would use to compute Ext. For example, if you have two complexes of injective sheaves, then Hom between them has a natural differential on it, and that's exactly the one we take. And then we have a composition map mu2 defined at the chain level. And then all the higher ones are 0. Okay, so Is this visible? This is a special kind of A infinity category called a DG, or differential graded. Category. So there's this slightly funny looking asymmetry between the A model and B model, that the A model has all these A infinity maps, whereas on the B model you have mu1, you certainly can have differentials and you can have composition maps when you're computing x's between coherent sheaves, but there's just mu greater than or equal to 3 doesn't fit into the story. Nevertheless, we're going to regard this as an A infinity category. So it's compatible with what we're doing on the A model side. And I should say that there are general theorems by Luntz and Orlov that basically say that this sort of, there are many ways of choosing a DG category underlying your category of bounded derived category of coherent sheaves. But as long as the cohomological category you get is the bounded derived category of coherent sheaves, this is basically these choices are all quasi-equivalent. A infinity, well, DG quasi-equivalent.
So your choice here was to fix the injective resolution?
Yes. But you could also, for example, choose to use check, a check model for your X'd groups, and just have the check differential and the shuffle product between co-chain level check complexes computing X'd groups.
Is there a ground version?
I would, yes. In the complex analytic case, I think that, anything that computes the right category should be quasi-equivalent, no matter how you come up with it. So yeah, I think there should be no problem setting up a de Rham version of all your X'd groups and composition maps. Okay, so now this is where I would have said this thing, that the statement of homological mirror symmetry, then if M and M check are mirror varieties, is that some kind of derived version of the Fukaya category is A infinity quasi-equivalent to the A infinity category of bounded derived category of coherent sheaves on M check, where this one turns out to have all the mu greater than or equal to 3 equal to 0, but that doesn't play any role in the statement. We just act as if they could be there. So maybe I should say there's a general procedure called taking twisted complexes there's a general procedure called taking twisted complexes for forming the derived category of an A infinity category. So that's what we've done here. I defined the Fukaya category, but to have a hope of homological mirror symmetry being true, you need to take some derived version of it. But there's a very sensible way of doing that. That's called taking twisted complexes. And if you take the cohomological category of this A infinity derived version, this has a natural triangulated structure. So if you've heard of this this problem of cones being non-functorial in triangulated categories, these A infinity categories, or I mean, many people also just stay to the world of DG categories. These are a way of fixing that problem, basically. So, for example, an efficient way of computing the Fukaya category is finding some subcategory so that when you take the derived category of that subcategory, you get everything, so it somehow generates. And this is not something you can do. It's not, you don't have enough sort of information in some small subcategory to do this if you're only working with ordinary abelian and triangulated categories and so on. So this A infinity formalism actually makes things a lot nicer. I haven't talked about that at all. This is, yeah, I mean, so it looks like a sort of vacuous statement because it says, you know, the hypothesis is that, you know, sometimes this is true, and of course, you know, sometimes might include never. It's really saying there are lots of interesting examples of this. And there are some procedures for constructing manifolds that ought to be mirror to each other, which have dual Lagrangian torus fibrations. But I'm not going to get to talk about that. So, okay, I'm going to skip that. So we saw this closed open map from quantum cohomology of M to Hochschild cohomology of the Fukaya category. This was how we related the open and closed string invariants there. The analog of this in the B model is the Hochschild, Constant, Rosenberg isomorphism. Often shortened to HKR. So where does that come from? So there's a DG category, DG functor from the DG category of coherent sheaves on X cross Y to the DG category of DG functors between dBco of X and dBco of Y via viewing an element in here as a Fourier-Mukai kernel. All of these need to be the appropriate, well, DG version. You always need to stay in the world of complexes and on the cochain level. And the structure sheaf of the diagonal corresponds to the identity functor under this correspondence. Now, the Hochschild cohomology of our DG category is the endomorphism algebra in the category of DG functors from dB co of x to dB co of x of the identity functor to itself. I mean, I guess I have to basically say this is more or less by sort of by unwinding the definitions. And I mean, I gave you an explicit cochain level model for this Hochschild cohomology, but that can be sort of tautologously related to endomorphisms of the diagonal bimodule of this category, and that basically turns automatically into this thing. The actual theorem we need is a theorem of Toen, which says that this DG functor here under mild conditions on x and y is actually a quasi-equivalence, which means that endomorphisms of the identity in this category are isomorphic to endomorphisms of the structure sheaf of the diagonal, which corresponds to the identity, in this category here. Which, okay, I feel like a bit of a fraud because I'm just copying this from a paper, but this turns into and now this is the, oops. This is essentially the Hochschild-Costant-Rosenberg isomorphism, that this sheaf is isomorphic to this complex of sheaves with trivial differential, just the algebraic differential forms of degree I in cohomological degree I, with no differential between them. This is essentially what Hochschild-Costant-Rosenberg proved in the affine case, and then I think it's due to Yekutieli that this is also true in the it can be sheafified, and it's also true in the non-affine case. So that means that it's equivalent to cohomology of polyvector fields, since this is just taking the dual of these sheaves here, which is exactly what we defined our tangential cohomology to be. So from general results, this Hochschild cohomology of our category is isomorphic to tangential cohomology of the underlying variety. So that's the analog of this closed open string map that we had on the A model. Okay. So now that we've kind of seen a very I don't know, sort of high-level picture of what homological mirror symmetry is and how it's meant to imply closed string mirror symmetry. I want to spend the rest of the time doing a bunch of examples.
You were assuming that space is non-singular?
Yes, it's, I mean, this theorem of Toen that this functor is actually an equivalence requires quasi-projective non-singular, I think. But, you know, okay, here I also feel like a fraud. I don't know the theorem very well. So one of our simplest examples of homological mirror symmetry was, or of mirror symmetry, was that C star is mirror to itself. So we can take this Lagrangian inside C star, just the circle. Its Floer cohomology is just isomorphic to polynomials in one anti-commuting variable theta. And in fact, one of the things that makes this a particularly simple example is that there's no higher A infinity structure in this case. On this side, we have C star, which we'll draw like that. And the mirror to L here is the structure sheaf of a point, OP, or skyscraper sheaf at a point. So this is an affine scheme, so x's of sheaves are just x's of modules over the the thing it's spec of, the coordinate ring. And the module corresponding to the skyscraper sheaf at a point is S mod Z minus P, where P is the point. So we can take a projective resolution of this guy, and then we get something with two one-dimensional summands and no differential between them. This one in degree 0, this one in degree 1. And you can check, well, it's obvious. I mean, this is, so you're always going to have that in the endomorphism algebra of a sheaf with itself, you're going to have an identity element, which is going to multiply to everything, like an identity. And then the non-identity one is in degree 1. So when you multiply that with itself, it would live in degree 2, but there's no degree 2, so theta squared must be 0. And again, there's no higher A infinity structure hiding in there. Okay, here's another example. So it's using something I haven't said very formally, well, haven't said at all, but when you have a non-compact Lagrangian, one way of taking its flow cohomology is to apply some Hamiltonian flow that wraps it infinitely many times around and then intersects it. So this is called wrapped flow cohomology and is the right thing to do in this case. And it turns out that this endomorphism algebra of this Lagrangian is isomorphic to C of Z, Z inverse as an algebra. So this would be like 1, this would be Z, this would be Z inverse, and so on. And this corresponds on this side to the structure sheaf O, whose self X are just S itself, which is C of Z, Z inverse. So again, they match up. And again, there's no higher A infinity structure. So there is more to check than what I've just said. Maybe I should have made this one L prime. So, I mean, I'm not claiming to have given a complete proof that these categories are A infinity quasi-equivalent, but in this case, this is a theorem. And this Lagrangian L I drew here maps to the coherent sheaf OP under the quasi-equivalence, and L prime maps to the structure sheaf O. Okay.
So So there's a model for the categories where these are the only objects?
No, I'm saying that there's a model for the. I mean, these categories have a lot more objects in them.
Okay.
I'm just giving you an example of some how some small parts of the categories match up. Okay. So one of the first, in Koncevich's original talk or article where he outlined homological mirror symmetry, he already suggested looking at the case of the elliptic curve, and indeed things work out really nicely there. So, and this was worked out in a lot of detail in a paper by Polishuk and Zaslow. So in this case, we want to take our symplectic manifold to be just a torus of area 1. And we want to take our dual manifold to be this family of elliptic curves. So I know this looks a little strange, but in fact, what this really looks like is that we should be doing rigid analytic geometry, and indeed that seems to be sort of somehow the correct framework for doing mirror symmetry, because this doesn't look sort of like a standard way of describing an algebraic variety. But it's the right one for mirror symmetry. But maybe I could just explain that the reason we want to have a family of varieties here is that we want this we want to think of this as a variety defined over the Novikov field lambda, which was formal sums of real powers of a single variable r. So you want to think of this family of varieties as being defined over this Novikov field. Well, really, it's most naturally defined over formal power series, and then you want to tensor, do a base change to this Novikov field. And And the reason we want this mirror variety to be defined over this Novikov field is because on the Fukaya category side, we've seen that it's very difficult to avoid defining the Fukaya category over the Novikov field. So this is some lambda linear category. So if over here our variety M check were just some complex variety, then its category of coherent sheaves would be some complex linear category. It wouldn't be the same kind of thing. We wouldn't be able to compare it. So it makes sense that it's defined over lambda, and indeed, you know, mirror symmetry is really about families of varieties when we're in the closed case like this.
Always one parameter families, is that right? Because lambda involves one variable?
No, it should be about more parameters. You should be able to, so on this side, you should be able to think about a family of symplectic forms. You know, if H2 of your manifold has some, is 10-dimensional, then the moduli space of symplectic structures is 10-dimensional, and the Fukaya category should somehow live over that moduli space of symplectic structures.
Oh, I see.
And then on this side, you should take some sort of it's not the universal family, but a family of complex manifolds over the moduli space of complex structures on your manifold. So a family of coherent sheaves defined over the space of complex structures on your manifold. The reason we only defined it over lambda with a single variable is for technical reasons, that defining the Fukaya category with more parameters like that gets technically complicated.
Oh, I see. But it's a complexity you want. You didn't do it for expositional reasons.
No, I did it because it's a technical complexity. That I'm not sure. Yeah, I'm not sure what exactly the correct way to work around it is. What one can do versions of the Fukaya category with more parameters, but they're conceptually a little bit different from, just a family defined over the moduli space of complex structures. So I've left that stuff out. Yeah. Okay. So now on our elliptic curve, we're going to have L0 L1 and LP, where P equals A plus IB, and A is, or maybe I should say P equals e to the A plus IB is our complex number, sort of parameterizing this choice of this Lagrangian here. So A is this distance of LP from the origin, in this direction. And e to the IB gives us a local system, a U1 local system with monodromy e to the IB. So I mentioned this only very briefly in a previous lecture, that you can enhance objects in your Fukaya category by putting local systems on them, and then every time you count disks with boundary on that, you weight the count of disks by the monodromy of the local system around the boundary. So here L0 and L1 just have trivial local systems, but for every disk we count, it will be weighted by the monodromy of this local system with monodromy e to the IB along the part of the boundary the disk passes along. So we have a generator E0 for fluid cohomology of L0 with LP, and we have a generator S for fluid cohomology of L0 with L1, and a generator I'll call EP for wait, have I got this the right way around? Yes. Okay. And we're going to be interested in calculating the coefficient of E0 in mu2 of S with EP. Okay, and what's the mirror to all this? We have this family of elliptic curves we're going to take three coherent sheaves that are going to be mirror to these three Lagrangians L0, L1, and LP. So mirror to L0 is the structure sheaf O. Mirror to L1 is a line bundle L, which has first Chern class equal to 1, and mirror to LP is the skyscraper sheaf at R to the A, well, I'll call this Q, R to the A, E to the IB in this elliptic curve M check sub R. And mirror to this composition mu2 of S with EP. So is the composition of some section S of the line bundle L with evaluation at Q of in some chosen trivialization of L at the point P. And the composition of these guys is the value of the section at Q in whatever local trivialization you've chosen. Okay. So to work out all of the holomorphic triangles which will contribute to this product mu2, the best thing to do is to draw the universal cover of our elliptic curve so we can see all the immersed triangles. So here's S, and right here are our copies of E naught. Here are our copies of EP. So you can see you're going to get an integer's worth of holomorphic triangles contributing to this A infinity product, mu2 of S with EP. So here we get an A infinity product with S, then EP, giving some contribution to E naught. Here we get one giving a contribution with S, then EP, then E naught, and so on, bigger and bigger. Tells us that mu2 of S with EP is the sum over all integers of R to the symplectic area of the triangle UK times monodromy, something like that, of this local system, which has monodromy e to the IB around the whole thing, but we'll only be looking at the monodromy around one part of the boundary, times E naught. So this bit I haven't said before, but I'll just write down the term that goes in there. But this one we're familiar with, that you have to weight all your counts of holomorphic disks by R to the symplectic area. So what is the symplectic area of this guy? Well, the side length of this triangle is always going to be A plus K. So its area is going to be half A plus K squared. The monodromy, well, the monodromy going around length 1 is e to the IB. So the monodromy going around a side length of length A plus K is e to the I A plus K B. This all times E naught. So we can take some of the constants out the front. Sorry. So we see this this Q appearing again, R to the A, E to the IB, and this F of Q is now a recognizable function . So it's the sum of R to the half K squared Q to the K. And we note that F of R times Q is equal to which is equal to so F of R times Q is R to the minus a half Q to the minus 1 times F of Q. So this is the kind of functional equation that theta functions, which are sections of line bundles on elliptic curves, satisfy. So we set L, the mirror to L1, to be the line bundle whose total space is this. Where the monodromy of this line bundle, so acting on this C factor under this multiplication by R, which is one of the directions we can go, one of the generators of first homology of the elliptic curve, is R to the minus a half Z to the minus 1. That gives the monodromy of this line bundle. And it's well known that, you can always make the monodromy in the other direction trivial, which is why I've written it in this way. So in particular, sections of this line bundle written in a local trivialization have the form S of Z, some infinite sum of powers of Z satisfying some periodicity property, but not just periodicity twisted by the monodromy of the line bundle. So we get exactly this functional equation that we saw was satisfied on the mirror side. And in particular, this functional equation gives a recursion for the AK in terms of AK minus 1. So there's exactly one section, there's exactly one function like this up to scaling. So the space no, that's, yeah, okay, that's true, yeah. So there's the space of sections of this line bundle. Well, there's no higher x's because it's ample, so x is just the same as sections of the line bundle L, and the space of sections is one-dimensional, just like the space of Homs in the Fukaya category between L0 and L1 is one-dimensional, given by this intersection point. So more generally, if you have a Lagrangian of slope k, here's one of slope 3. So L naught's up here. Well, not C. Then you have a 3-dimensional space of HOMs between L0 and L3 in the Fukaya category. And similarly,
K is an integer?
yes, K is an integer here. But the space of HOMs So the space of HOMs, or of X, is again just the space of sections. There are no higher X's because this line bundle is ample. So it's the space of functions S of Z, sum of A k Z to the K, where S of R dot Z equals R to the minus K onto Z to the minus K S of Z. So now you're going to get a recursion for the coefficients A. Oh, sorry, I've used K twice. Let me use J. Well, okay, actually maybe it's more efficient the other way. Okay. All right, so now you get, from this functional equation, you'll get a recursion for Aj in terms of a j minus k. So as soon as you specify the first k coefficients, everything else is determined uniquely. So this is a k-dimensional space of sections, just like this this space is k-dimensional. There are k intersection points of your Lagrangians. And again, these sections are called theta functions, and I mean, are well known in algebraic geometry. And now you can start asking what happens when you multiply these theta functions together. So for example, if you have so you might take some theta function in here and want to multiply it with a theta function in here to get a theta function in this space. And there are all sorts of classical formulae for how to do this. And of course, in the symplectic geometry world, this corresponds to taking some intersection between these Lagrangians and counting triangles weighted by their areas. And you can check that everything matches up. So there's something kind of non-trivial that that actually matches up on the two sides. It's all these identities for multiplying theta functions. Okay, I guess it's 5, so I'll stop there.
Thank you very much for